Hi, I'm Marco Panizza. I'm the European Application Manager for Vicor. Today I'm going to discuss with you the challenges involved in designing power supply systems for civil and military aerospace application. And also I will show you how to meet the demanding requirements of these kind of applications. It's obvious that aerospace applications need power solutions that deliver high performance with small size, lightweight, and high power density to meet the physical constraints imposed on any electrical system that will be used in flight. Reliability is another critical factor. Whether the electronics are required to ensure the airplane continues to fly safely, or the cost of replacement is unacceptable, for example in a satellite, aerospace applications demand products with extremely high reliability. Systems also need to meet other demanding criteria. If the power supply is not housed within the cockpit, then it might be subject to extreme of heat and cold, requiring a wide operating temperature range and efficient heat sinking. However, often it's the electrical requirements which present the most challenging issues to the designer, in specific the EMI requirements for aerospace application. The most common standards that defines these requirements are the Mill Standard 461 and Mill Standard 704. There are, however, other standards for more specific application. For example, the Airbus aircraft lines must meet specific standards from the Airbus industries. In this video, I'm going to show you how to meet those requirements and design a power supply system based on our Mill VI chip family. EMI is divided into two parts, conducted and radiated. Conducted EMIs are voltage and currents that flowing into the leads of the power supply systems. These can also be divided into two subparts, which is common mode and differential mode. Common mode disturbance, or EMI, are currents flowing in the same phase on both the positive and negative input leads. Differential EMIs are components flowing opposite in phase on the plus and minus input leads. There are many different measurements that are defined in the standards, so I look at just one, the CE102 limits for Mill STD 461. This measures conducted EMI into 50 ohms. I have translated the limits into millivolts, and you can see that the requirements get more stringent at higher frequencies. Radiated emissions are due to currents flowing in a suitable antenna, frequently the power leads, in the device under test. Radiated emissions can be reduced by reducing the conducted emissions. They are also affected by the device enclosure, lead geometry, and other devices operating nearby. Conducted emissions can be reduced by using an input filter. Systems often require a multi-stage filter to achieve the required attenuation. This filter provides series impedance that reduces both common mode and differential mode EMI, shunt impedance for common mode, and shunt impedance for attenuation of differential mode noise. It is good practice to keep the Q of the inductors and the ESR of the capacitors low for good attenuation without creating a resonance, or as it is sometimes called, peaking. Layout of the filter is also very important to avoid inadvertent parasitic coupling. Typically, engineers will measure the electrical characteristics of the device to allow calculation of the optimum component values. More information about these calculations is given in the application note number 22, which is available on the vicorpower.com website. Although a filter will attenuate transients, military applications requires more stringent immunity to spikes and surges that cannot be achieved with a simple input filter. In this case, the solution is a more complicated structure which is dependent on the kind of specification that needs to be met, and in turn depends on the kind of application that is being implemented. For new aircrafts, normally the Mill Standard 704F applies. In this case, the requirement is fairly benign, and a standard military PRM with an input range from 16 to 50 volt will meet the specification. For older military aircrafts, The standard that applies is the Mill standard STD 704A, which has more stringent requirements. In this case, the PRM will require an additional protection system in front. Usually, this is achieved using an input shunt transorb to clamp the spike to a reasonable level, followed by an active clamp circuit. This diagram shows a typical clamp that uses FETs to reduce the voltage to the output to the minimum level the DC device can tolerate. In this circuit, Q1 is the main clamping element and must be sized to handle the power dissipation needed. Although it is perfectly feasible to build a clamping circuit using discrete components and design the EMI filter, most engineers choose off-the-shelf solutions such as Vicor's M-FEM7 or perhaps a combination of the FEM7 with transorb for the most demanding situations. Using an off-the-shelf solution will save time and ensure compliance, reducing the development risk. There is a lot more information at vicorpower.com. In addition to product technical data, you can access our extensive technical library and get more information on civil and military aircraft applications, or improve your knowledge on power supply design by taking our video tutorials. In alternative, you can send an email to videos@vicorpower.com and I will be glad to help you out and answer all your questions should you have. Thank you for watching and don't forget to check out our other videos.